Until today, most of them F-47's specifications remain classified. Yet strangely, analysts are beginning to understand how this aircraft is likely to operate. Not through leaked photos or internet rumors, but through physics, mathematics, Boeing's technological developments, and the highly classified Next Generation Air Dominance NGAD program, whose details are gradually coming to light. Design philosophy. While previous generations of fighter aircraft focused primarily on avoiding radar detection, the F-47 is believed to be designed to survive across the entire spectrum of modern warfare. That means its design is expected to consider far more than radar alone. It is also likely optimized against infrared sensors, satellites, electronic warfare systems, and cooperative operations with autonomous drones. In other words, it is no longer just a stealth aircraft. It is designed to function as part of a highly connected combat network. This represents a fundamental shift in the design philosophy of modern military aviation. Evidence from Boeing. Although details about the F-47 remain limited, Boeing has spent years developing technologies that align closely with next-generation fighter concepts. The company has extensive experience in stealth design, digital manufacturing, advanced composite materials, and unmanned aircraft systems. It has also introduced manufacturing methods that are significantly more automated than those used just a few decades ago. Robots now assist with drilling, panel assembly, and precision inspections. In other words, innovation extends beyond the aircraft itself. It also transforms the way the aircraft is built. The engine, more than just power. Beneath the airframe, the F-47 is widely expected to feature a new generation adaptive cycle engine. Unlike conventional jet engines, this technology can alter its airflow configuration depending on mission requirements. When efficiency is the priority, the engine reduces fuel consumption. When maximum performance is needed, it produces significantly greater thrust. This capability enables the aircraft to perform supercruise, sustained supersonic flight, without continuously relying on an afterburner. The benefits go well beyond speed. Fuel efficiency improves, operational range increases, and engine heat can be managed more effectively through advanced thermal management systems. This is especially important because excessive heat makes an aircraft easier to detect with infrared sensors. Technologies working together. The F-47 is expected to integrate three key technologies: stealth, artificial intelligence, and collaborative drones. The aircraft is no longer designed to operate alone. Imagine a pilot commanding several drones flying ahead as reconnaissance platforms, additional sensor carriers, or even weapon platforms. Meanwhile, artificial intelligence processes thousands of pieces of information within seconds. The pilot still makes the final decision, but the analytical workload that once required much more time can now be completed far more quickly. The physics behind stealth. Many people assume that stealth means an aircraft becomes completely invisible. In reality, it does not. Stealth is an application of physics. Radar works by transmitting electromagnetic waves. When those waves strike an object, part of their energy is reflected back. If the reflected signal is strong enough, the radar can detect the aircraft. For this reason, the F-47 shape is believed to be carefully engineered so radar waves are redirected away from the radar receiver instead of reflecting directly back toward it. Some of the incoming energy is also absorbed by radar-absorbing materials. In addition, different radar wavelengths possess different detection capabilities. The more sophisticated the combination of aircraft geometry, materials, and reflection angles, the smaller the probability of detection. Stealth is not magic. Stealth is the result of engineering based on the laws of physics. Mathematics that shapes the mission. Why is a combat radius of around 1,000 nautical miles frequently discussed? Because range determines strategy. In modern air operations, every additional kilometer expands the number of available routes and operating bases. Behind that capability lies extensive mathematical modeling. Engineers calculate the fuel fraction, the ratio of fuel weight to total aircraft weight. They estimate the probability of kill to predict mission effectiveness. They model radar detection probabilities and optimize flight paths to minimize exposure to high-risk areas. All of these calculations are performed using mathematical models before the aircraft ever leaves the runway. Algorithms, the digital brain on the battlefield. If drones are expected to operate alongside the F-47, how do they determine the best route? The answer is algorithms. Drones perform path planning to identify the most efficient flight route. They use obstacle avoidance algorithms to steer clear of threats. They apply sensor fusion by combining data from radar, cameras, and infrared sensors into a single operational picture. Artificial intelligence then assists with target prioritization, determining which targets are most critical based on the evolving tactical situation. Some systems are even expected to employ machine learning and reinforcement learning, allowing them to adapt to changing battlefield conditions over time. This is where computer science becomes an essential component of modern warfare. Materials and chemistry. Much of the F-47 structure is expected to be built using carbon fiber composites and sandwich composite structures. These non-metallic materials offer exceptional strength while being significantly lighter than conventional metals. More importantly, they reflect far less radar energy. However, producing materials like these is not simply a matter of mechanical engineering. Behind them lies the science of materials chemistry. Everything from advanced resins and carbon fibers to radar-absorbing coatings is engineered to reduce the amount of reflected electromagnetic energy. Even modern aviation fuels and lubricants are the result of continuous advances in chemical engineering. MCON and the strategy of the future. The F-47 is also expected to employ emission control, or EMCON. This means the aircraft does not continuously operate its radar, radios, communications systems, and data links at the same time. The fewer electronic emissions it produces, the lower the chance of being detected by an adversary's passive sensors. This strategy is becoming increasingly important in modern operational environments, particularly in regions such as the Indo-Pacific, where extensive radar networks, layered air defense systems, and anti-access/area denial (A2/AD) strategies are expected to play a major role. This is where the F-47 is believed to operate alongside collaborative drones, GPS satellites, ISR networks, and a wide range of supporting systems. Closing. So, is the F-47 truly invisible? The answer is no. Low-frequency radar can still provide indications that a target is present, although with limited precision. In addition, multi-static radar networks, infrared sensors, passive electronic surveillance systems, and the fusion of multiple sensor types continue to evolve, steadily improving detection capabilities. The objective of stealth technology has never been to make an aircraft disappear. Its purpose is to reduce the enemy's ability to detect, identify, track, and successfully engage the aircraft. Looking ahead, many analysts expect the F-47 to continue advancing through next-generation radar-absorbing materials, improved infrared signature management, increasingly sophisticated electronic warfare systems, deeper integration with collaborative drones, and artificial intelligence that assists tactical decision-making. And perhaps it is precisely the technologies that remain classified today that will shape the future of air warfare in the decades to come.